And thank you all for coming. It's really great to be here. I haven't actually been at Stanford that long, so this is my first time. I'm really excited to get the chance to present here. As Marco said, I want to shift focus a little bit from the private sector to the nonprofit sector. So when I was a grad student, I was working at the interface between scientific computing and earth science. And as part of this PhD work, I went to my first computing conference. And after listening to some of those high-performance computing talks, I couldn't help but feel that I walked into a bodybuilding studio. A, it was mostly men sitting there and talking, and B, everyone was talking about power, computing power. So you might imagine that I felt a little lost, because all these codes were running on these amazing clusters, and I had written all of my own code, and instead of running on 200 or more cores, it ran on my tiny little laptop. But when I presented my work, this guy came up to me afterwards, and he told me, well, you know, what you lack in high performance, you certainly make up in high purpose, which is kind of cool, and maybe we should be doing more of that. So what I'd like to convince you of today is that there's room for both in modern computing, and that we really should be thinking about both avenues of investigation. And what I would like to do is showcase a few examples of what I would like to think of as high-performance computing, as high-purpose computing. Because just as quite ordinary codes can be very extraordinary, we're learning in our work that some of the most extraordinary processes on Earth, like massive events like ice sheet disintegration, volcanic eruptions, or earthquakes, sometimes really hinge on extremely ordinary and small processes. So I want to start our journey into the extraordinary today with something extremely ordinary, an ice cube. We all have them in our fridges, we use them day to day, melt them down every day. So by experience, we're all experts on ice cube melting. Let's see about that, because here is the biggest ice cube we currently have, the Antarctic continent. And when you think of it, it's really just that, right? It's a massive amount of ice sitting there surrounded by warming waters and melting away. So it seems obvious that when you think about the future evolution of this massive ice cube, you would think of it just like you think of the baby brother in the water glass. Interestingly, though, Antarctica melts in a fundamentally different way. And we know this from satellite images like this one. And what you see here is the speed with which the ice is flowing towards the coast. So in the blue area, it's barely moving. And in the red areas, it's racing along, and it's almost 3 magnitudes faster. So to put that into perspective, that's a speed difference that's kind of similar to a very slow pedestrian and an extremely fast Formula One car. So it's more than just a little bit faster. And you can also notice that the spatial distribution isn't that of an ice cube either. Instead of gradually melting away from the edges, these artery-like red zones you see here on the slide actually already drain ice from the center of the Antarctic continent. So in a way, the way that Antarctica is melting is not from the inside out, is not from the outside in like a regular ice cube, but from the inside out. So exactly the other way. Now, as if that wasn't surprising enough, the biggest puzzle is actually still to come. Because what we've also learned is that there's an even more extreme variability in the temporal behavior. So let me zoom into one part of Antarctica, which is the Sibel Coast. And in the Sibel Coast, you can see 5 of these arteries. And we care so much about them, we gave them names. And I want to focus your attention on the blue blob right in the center of the slide, which is labeled as CAM. So obviously it's not doing much at the moment, but it turns out that until 200 years ago, it was an artery, just like the other ones. It was flowing just as fast. And then suddenly, it just stopped. It just went away, which to me still seems more like magic than it is science, but the data very clearly shows that. And by discontinuous, I mean probably in less than a year or so. And prior to climate change and all of this wonderful data, we thought that ice sheets couldn't respond faster than a few hundreds or thousand years. So having adjustments on a yearly timescale is extremely surprising. So what that means is that these arteries in Antarctica are not like the arteries in your body. They move around, they stop, they start, they accelerate, they slow down, they do crazy things, they multiply, right? And that's what we need to understand. So what the heck is going on? In which way is this huge ice cube so very different than its little brother in the water glass, right? They're both ice, they're both surrounded by water. The big difference is that Antarctica has a subsurface. It actually sits on ground. So let me peel away the data layer that shows the ice velocity and just have a look at that subsurface. Here it is. The first thing you might notice is that it's extremely flat. So I guess, had I showed you this slide at the beginning, you couldn't have guessed where the fast flow is occurring as opposed to the slow flow. So what that means is we have ice flowing down a plane, and for some odd reason, it doesn't flow equally everywhere, but it channelizes extremely in very narrow zones. So how can we possibly understand that, and how can the subsurface create that? Because it's not variations in the nature of the subsurface. It's not obvious from this graph, but we're very certain it's the same kind of sediment underlying this entire area. And the answer to the puzzle is water. Is the interaction between water and sediment grains underneath the ice. So how can a process like that, tiny, delicate like that, really have this kind of an impact? Let's return to a more familiar and ordinary environment to understand that. Let's go to the beach. Here's a beautiful sandcastle, and I'm not sure whether you ever tried building one of these. It's not actually that easy, but the trick is to get the water content in the sand just right. Because if you change the water content of the sand, it goes from completely solid to completely fluid. And that's kind of astonishing, right? Other materials don't do that. You can't fluidize the rock by pouring water on it. So it's really astonishing that sand has this material, and that's this property, and that's true for sand, but that's also true for other sediment, and that's ultimately what's happening in Antarctica. Because as ice is flowing down the plain, it rubs against the sediment a little bit. And this rubbing creates meltwater. And this meltwater makes the sediment weak and basically just tears away the subsurface underneath the ice. So that is what facilitates this really fast flow. Interestingly, though, water is both the engine and the brakes of this process. Because what happens if you add more and more water is the water stops distributing equally. And you know this from a rainy day, right? When it starts raining, the first thing that happens is the entire ground gets wet. But as you add more and more water, the water begins to channelize. You have lakes, little channels or accumulations of water. So what that means is you have a patchwork in the subsurface that relates to a patchwork in stability and instability. And that's what's governing these extremely interesting flow patterns. And that can also help us understand why there's such an extreme temporal variation in these flows, because the temporal scale over which these arteries change is governed by water, not by ice. And hence it can adjust extremely quickly. Now you might think that, Antarctica is kind of unique that way, right? It's maybe just a weird coincidence and it doesn't really generalize to anything. So let's switch to a different system and think about the same kind of problem. So here is the tsunami in Japan hitting the shore. And we think of tsunamis as water waves, right? Just like we used to think about Antarctica as ice cubes. But when you have a look at this picture, it sure looks like a water wave out there, right, before it hits the coast. But once it hits the coast, it no longer looks like a water wave. And it really doesn't make sense to think of it that way. It turns into a current, it turns into white water, and as we move in even further, it turns into this really ooey gooey, horrific monster that just propagates and eats up everything and anything, the houses, the cars, the sand, everything and anything. But what that process means is that it gradually changes the nature of the phenomenon. So not even the destructive power of a mega tsunami can resist the transformative nature of sediment-water interactions. And that's important to think about, because if we want to find ways to reduce the reach of these tsunamis, and we have all of our coasts covered in concrete, we might be creating more problems than we solve. So we are working on trying to understand the onshore propagation, take into account this transformative effect that the interaction of sand and water and gas has. Now, both of these extreme events, tsunamis and ice sheet disintegration, are kind of far from your daily experience, I'm guessing. So let's return to a topic that's closer to home: earthquakes. We're the earthquake capital of the US, right? We like a little bit of shaking. But it turns out we have competition, and we have competition from a very unexpected place, Oklahoma. Here's the number of earthquakes in Oklahoma with magnitude 3 or greater, which means you can feel these. Notice anything unusual? This doesn't seem to be much happening until a few years ago. And then Oklahoma really lit up big time from a seismic point of view, right? What you're looking at here is the consequence of our interventions. These earthquakes are created by wastewater injection into the subsurface. So very much like the Antarctic rapid flow is created by the interaction between water and sand grains, this kind of extreme event, these earthquakes are created by the effect that the wastewater has percolating into a rock formation and just making it slippery and prone to failure. So by adding this water, we basically turned Oklahoma into an earthquake generator, which is a pretty interesting effect that we might not have anticipated, certainly not at this level or at this level of magnitude. So what is the common feature between all of these examples? The unifying thread between all of these is that we care about understanding processes that help us reduce the danger of lives that are at risk from natural disasters. So we're trying to protect people basically from the impacts of big tsunamis, from the impacts of sudden sea level rise, from the impacts of these kinds of earthquakes by thinking about the processes that create these instabilities that are expressed in these extreme events, and by thinking about what the role that human intervention in a direct or indirect way has on these. And I think there's a lot of potential to carry this forward. And it's not just a high-performance computing problem, because very often we don't quite know what equation to solve in the first place. Right? I think Antarctica illustrates that, because the big ice sheet models assume it's all ice dynamics, but it's not. The rapid ice flow is really a sediment dynamics problem, and it's just expressed on the surface through the ice. So once we know what kind of equations we want to solve, yes, all we need is resolution, order, and accuracy to kill it. But prior to that, we really need insight into the physical processes. So that's why we're working on trying to understand these physical processes that will ultimately then be fed into these bigger scale models. So thank you very much.